Hello ladies and gentlemen, welcome to Chapter 15, Probability. Today we're going to be talking about empirical probability and theoretical probability. This is Chapter 15, Section 1, and also Section 2. There's a lot of notes here involving vocabulary. It's very important that you take down all these notes. I'm going to read through them with you. Please pause the tape if you need things to slow down so that you can get caught up. Probability is the chance of some event occurring. It is typically a fraction. So if we call probability of an event, we will do this down below. It has to be between 0, which is an impossible event, and 1, which is the probability that an event happens every time. It is a fraction between these two values. Empirical probability is derived from doing trials. An example of empirical probability would be flipping a coin 100 times and recording the number of heads you get and the number of tails that you get. Standing at a street corner and marking down hash marks on a page representing the different colors of cars that you see, or whether they're cars or trucks or motorcycles, those would all be trials. It's from witnessing it in the real world. And we call those trials experiments. The fancier, I guess, the trials become, the more likely we are to call it an experiment versus just a trial. Relative frequency are values from one small set of trials. You may flip a coin 100 times and you may get heads 40 times, and you might get tails 60 times. So you would say that the probability of getting a head is 40 out of 100, which reduces to 2 fifths. Now that is not the theoretical mathematical probability of getting heads, but in your very small set of trials, and flipping a coin only 100 times is a very small set of trials, here we would get a relative frequency of 40 out of 100, or a probability of 2 fifths. Now I'm going to erase this because that is just simply not true, and the more and more trials you do, or maybe we had every single person in class flip a coin 100 times. Now we're talking about 2,000 trials. And then we take all 3 of my classes and put them together, and now we're talking 6,000 trials. And we're going to start noticing a pattern as it's going to sort of trend towards what the theoretical probability of getting ahead when you flip a coin would be. Cumulative relative frequency. Value totals from all relative trials. So if you had the trials for student 1 and the trials from student 2 and the trials from student 3 and so on, cumulative relative frequency would be all those combined together. So I had the kid with the heads 40 and tails of 60, and then I had another kid that had heads of 30 and tails of 70, and I had another kid that had heads of 60 and tails of 40. And then when I combine all that together, I say, listen, heads, 40 plus 30 is 70, plus 60 is 130. Tails, 60 and 70 is 130, plus 40 is 170. If I made this, that would be a cumulative frequency, because I'm just combining all the relative frequencies together. Empirical probability equals the most accurate scientific guess of the cumulative relative frequency of any event happening. It's based on actual numbers, it's based on actual trials, but if you want that empirical probability to be accurate, you've got to do billions and billions and billions and billions of trials. Otherwise, it's not going to really approach what we would theoretically consider the answer to be. And that's basically what this says here. The more trials that you have, the better information or the better conclusion you can come up with, the more accurate that conclusion will be. All right. Notice, closer the cumulative relative frequency will converge on the actual probability. So your cumulative relative frequency is not correct. It's going to get closer to correct the more trials that you have, but it is not actually correct. It is not the theoretical actual probability, and we'll talk about how to figure that out. It's not hard. The actual probability isn't hard. And actually the hassle of going out and doing trials is actually more challenging than just figuring out the theoretical probabilities. Experiments can be affected by fair and unbiased objects versus biased objects. Should we have a new football stadium? If you go into the sports study hall on October 8th, which is in the fall, during fall sports, and you take a poll, that study hall is going to be full of football players. So if your poll is, should we build a new football stadium, you're going to get very different biased outcomes as opposed to just going to some random place in the community. Now, if you go to a bar in Pendleton, you're probably going to get some biased outcomes as well because, you know, there's no kids there. There's probably no families there. If you go to a restaurant that has a bar in it, you might be a little bit better off. If you go to the grocery store, not as many families. You're just getting the one parent doing the shopping. So it's really hard to come up with unbiased information. You have to be very careful about it, and when you set up trials, set up an experiment, you have to spend time thinking about, hey, listen, how am I going to be fair? How is this data that I'm going to get actually good data? I'll tell you what, there's a lot of really bad data out there, and you can use stats and probability to lie about stuff all the time using horrible data. All right, this right here, which I'll put in orange or boxed up in orange, this is the meat and potatoes of this entire chapter. The probability of some event happening. You take the total number of outcomes possible for the event. Like when I roll a die, it has 6 sides, so a die has 6 possible outcomes. A deck of cards has 52 cards, so there's 52 possible outcomes. And on top of that fraction, you put the number of favorable outcomes, and that creates the fraction which represents the actual theoretical probability. So, a 7 in a deck of cards. There are 52 cards in the deck, 4 of them are 7s. This reduces to 1 over 13. The probability of pulling a 7 out of a deck of cards is 1 out of 13. Diamonds. There are 4 suits in a deck of cards. They are hearts, diamonds, clubs, and spades. So of those 52 cards in the deck, 13 of them are diamonds. 1/4 would be this answer. Probability of the 7 of diamonds. Well, listen. There are 4 7s. There's a 7 of hearts. There is the 7 of diamonds. There is the 7 of clubs. And there's the 7 of spades. There is only 1 7 of diamonds in a deck of cards. 1 out of 52 would be the probability of getting the 7 of diamonds in a deck of cards. So there's some example of these. This is not empirical probability, this is theoretical probability, because if you pulled a single card out of a deck of cards for years and then recorded your results, I don't think you'd hit 1/13th. But you'd get close to that. You'd get close to it. You just wouldn't get it exactly. Alright, 4. Flipping of a coin. We want tails. Now there are 2 outcomes when you flip a coin. One of those outcomes is tails. The probability of getting a tails is 1/2. Theoretical probability. The number of ways that an event can occur divided by the total number of possibilities. So our formula from the previous page is how we compute a theoretical probability. Outcome, the result of any activity or experiment. So when we go back to this formula, if I flip back here real quick, and you can go and pause it at any time to write down those definitions. Outcomes. See the word outcome in this formula? So now we're defining what outcome means. The result of an activity or experiment. You take your deck of cards, you pull out a card that whatever's on that card is an outcome. You roll a die. Whatever number appears on top is an outcome. You spin a spinner, whatever number that lands on is an outcome. A sample space are all the possible outcomes listed together. So for a die, look at the curly brackets there. I get that. For flipping a coin, I would get that. So those are examples of sample spaces. Alright, an event is a subset of a sample space. So for example, that 7 of diamonds, that would be the set where the 7 of diamonds would be the subset of all the cards. Alright, your result for your probabilities that you're going to be setting up has to come from the sample space. Alright, singleton, only one outcome or way an event can occur. We'll see that in word problems sometimes. It's really not that big of a deal. only one outcome or way an event can occur is called a singleton event. So if you're only pulling one card out of a deck of cards, it's a singleton event. And when you do more than one, it becomes the probability becomes more complicated, and it's really not in this section tonight. So we have some vocabulary or some symbols we use to simplify things a little bit. That probability of an event from the previous screen, we call that P of E. Notice I said of. P of E is the probability of an event. N of E is the number of ways an event can occur. And N of S is the total number of outcomes in the sample space, or the total possible outcomes. This is the same formula that appears on the previous screen, or on the previous page if you're using your notes there. It's just written in symbols. Easy as heck to use. Looks very complicated. It's a nice fancy thing to pull out at the dinner table. Uniform probability. When you roll a die, if the die is not a loaded die, which means it's not set up by somebody to cheat, it has a uniform probability. There's an equal chance for you to get 1, 2, 3, 4, 5, or 6. When you flip a coin, if the coin isn't loaded, once again by someone who's trying to cheat, heads or tails has an equal chance of appearing. Alright, random selection, no special selection on our part. If you pull a little piece of paper out of a hat for a contest and they're all in there the same, that would be a random selection. If your friend says, hey listen, the one that's folded up into quarters is the winning number, you reach in there and you're feeling around, that's certainly not random. Alright, a fair coin is tossed. List the sample space. The sample space would be heads and tails. Those are the two possible outcomes. The probability of getting a head would be 1 out of 2. The probability of getting a tail, there's one tail out of 2 total outcomes. And that's where that comes from. There's one tail, there is 2 total outcomes. Here's our spinner. We have equal parts in the spinner. The sample space would be the numbers 1 through 8. B says list the possible outcomes in which arrow lands on an odd number. The odd numbers are 1, 3, 5, and 7. What is the probability of getting an odd? There are 4 odd numbers on the spinner. Of those, of the 8 total numbers, there are 4 odds out of 8 numbers. So 4 out of 8 is our probability. That reduces to 1/2. And that's it. You're certainly welcome to get started on the homework if you have some free time tonight, but we will be working on that in class. Have the best night of your entire lives, ladies and gentlemen. I look forward to seeing you on Monday.